Okay, great. So, welcome everyone. Also the people tuning in online. So today we have Tobias Hartung visiting us from London, and he's going to tell us about zeta-function regularization of expectation values.
Thank you very much, Chris. Thank you very much for the invitation. It's a great pleasure to be here. Now, I want to talk about something that kind of grew out of my PhD by accident. And in particular, I've been looking at zeta-function regularization of Fourier integral operators during my PhD, which is very interesting for a lot of people in geometric analysis. And basically, my problem is that I can't do geometry. So while I've been working on a problem that's been very related to geometric questions, I've always had a hard time finding workable examples. And so after some time, I basically gave up trying to find examples that people in geometric analysis are interested in. And I figured, well, I know a lot more about physics than I do about geometry. And physics has the same kind of structures. So let's give it a go. And well, I was visiting Carl at DESY at the time when I computed my first example, and for some reason I looked at the result and I went over to Carl's office and I was like, well, does that make sense to you? And he was like, yes, why are you asking? That's obvious. So at this point I figured, well, maybe this actually works on a more fundamental level than just trying to find examples for what I've been doing mathematically, and maybe there's some physics behind it. So I computed a few more examples and got physically reasonable results, which completely surprised me because everything we're going to be doing is completely unreasonable, at least from my point of view. And once I failed to find examples that I couldn't correctly, or from which I couldn't get physically correct results, Carl and I sat down and really looked into this and tried to figure out, well, what's actually going on here. So today I want to introduce you to, well, a zeta-regularization scheme for vacuum expectation values and why this makes sense physically. So let's start with the ropes. I know everyone here is probably well more qualified than me to talk about this, but let's talk about Feynman's work in 1948. The basic idea of Feynman's path integral is that, well, if I have a finite lattice, then for every path in the lattice, I have a quantum mechanical amplitude, and the probability density of the entire system is given by the sum of all paths, summing up the amplitudes mod squared. And one of the big points that Feynman put forward in the late 40s based on Dirac's work is that, well, actually, what people have been doing beforehand, trying to quantize this theory, try to figure out what this phi p is by hand, and getting stuck, essentially, you can shortcut this, and quantization is almost out of the picture. Because if you're quantizing a classical action, then the amplitude is just e to the I on h bar of the classical action along the path, which means we can now actually look at really large systems with lots and lots of paths, and in particular ask the question, what happens if I send my lattice to a dense approximation of the continuum? Well, I'm probably going to need some continuity assumptions on the paths because I'm trying to sample a function on a dense set. And I end up with an inductive limit procedure, which in his 1948 paper, Feynman showed to have a limit, a well-defined limit for naive quantum mechanics, and the Feynman propagator, which we probably more likely would call the path integral today, is precisely this limit. Now, this makes sense for quantum mechanics. This makes sense in an abstract setting using axiomatic quantum field theory. But in many interesting cases, we have no idea what this is supposed to mean, other than, well, there must be some inductive limit procedure that defines what these symbols mean. Yes?
What does the inductive limit mean?
It means that you have a net, and essentially you have a net of lattices, and the continuum, no matter how you discretize this into a lattice, you will have, well, whenever you project down to the lattice, you will get the correct version on the lattice. It's probably easier to be understood in terms of spaces. If you consider Sobolev spaces, then you have L2, you have W2 minus 1, W2 minus 2, and so on. And if you take all the W2 minus n's, the union will give you a space. And the topology on that is precisely the topology that you get if you take the topology and project it down to any W2 minus n. That'll give you the topology of W2 minus n. So this sequence of spaces inductively defines a topology on W2 minus infinity. And generalize that to more abstract settings and nets instead of sequences. So if we want to understand this, we probably want to talk about axiomatic quantum field theory a little bit, but before we get there, we also want to talk about what we're actually trying to talk about, and those are vacuum expectation values. So if we're in this lattice situation, then everything makes sense, and given a discretized observable on a Lorentzian background, you can follow the the steps that Feynman did in his book to obtain a expectation value, which is an expression of this form. And this makes sense distributionally. Numerically, you're going to have a hard time trying to evaluate this guy. So usually we put in a Wick rotation, put ourselves onto a Euclidean background, and then the i's will be turned into -1s. And now these integrals are absolutely convergent. You can do them numerically, and you get your expectations. The problem is, we can't always go down to Euclidean background. If you think about quantum field theories in curved space-time, you can write down space-times where no Wick rotation exists. There are other cases where they might exist, but we don't know how to do it. So we would like to, or I would like to understand what this guy means. And this is where we have to understand a little bit more about the distributional side on the path integral, and have to look at axiomatic quantum field theory, because those are the cases that tell us, well, where we understand what's happening, and then we can try to understand a little further what we're trying to do when we're talking about these distributions. So in axiomatic quantum field theory, on the most abstract level that I'm going to look at, we will have a Hilbert space, and we have a C0 group, which is our time evolution. Now, the time evolution is generated with a generator, which I'm going to call the Hamiltonian. And if you're using an axiomatic quantum field theory where the path integral is well defined, then it turns out that the path integral itself is the Schwarz kernel, i.e. a distribution which defines the time evolution. And that is why this only makes sense in a distributional sense in general, because this only makes sense in a distributional sense in general. And if you then continue on in this setting and again follow all the steps that got you to the vacuum expectation values in the first place, then now you're working with operators. Well, you end up with the expression where you have the trace of the time evolution acting on the observable and divided by the trace of the time evolution. And again, this is completely peachy if we're in a discretized setting, because these are matrices. This is also fine in the Wick rotated setting, because those will be traced as operators. So the trace, as in you take all the eigenvalues and you can sum them up in modulus, will exist if you then sum them up to get the trace. The problem is, if we're working in a Lorentzian background, then this is a unitary in an infinite dimensional vector space, i.e. it's bounded, but certainly not trace class. And this guy is generally an unbounded operator, so the question is, what the heck are these traces? And this is where zeta-regularization really comes to shine, because zeta-regularization is something that was born out of the idea that if you have an operator algebra, you want to know about traces. Because traces give you invariants, and so if you have an operator algebra that corresponds to, say, a manifold, then you will get invariant of your manifolds. You get geometric quantities out of it. If you do topological things, then you get topological invariants. Now, here, well, essentially, we're looking at algebras that are related to physics. So hopefully, we can get physical invariants out of our algebras once we've constructed these traces. And these could be the vacuum expectation values. So how does zeta-regularization work? Well, on the most abstract point of view, you have some operator algebra. We're going to have to reduce the number of algebras that we can look at here quite significantly in order to make sense of anything. But in general, we have some operator algebra, let's call it A, and we have a subalgebra, let's call it A sub 0, which is good in the sense that we already know a trace which is continuous on this subalgebra. In our case, this will in general be an algebra of Fourier integral operators, and this will just be the trace on trace operators. Now, the point of the entire game is that given an operator A, which is in the large algebra, but not in the good algebra, then we want to define what tau of A is supposed to mean. And the idea is that rather than looking at A in isolation, I want to construct a holomorphic family phi that maps into the algebra, such that phi of 0 is the operator that I'm trying to look at. And the set of values which are mapped into the good algebra under phi has connected nonempty interior. If this is the case, then we can reasonably talk about analytic extensions of whatever tau composed with phi is supposed to mean. So if we can extend tau composed with phi all the way to a neighborhood of 0, then we have a shot at trying to define what tau is supposed to mean. So, first of all, the maximal meromorphic extension of tau composed of phi, I'm going to call the zeta function of phi, and that means we have two questions to answer. The first question is zeta phi holomorphic in a neighborhood of 0? If that fails, then we can't evaluate in 0, which means we don't have a candidate for tau of A. However, even if this is the case, then we still have to answer the question, well, what if I take a different holomorphic family to say psi, such that psi of 0 is also my operator A? Well, then I have two candidates for what tau of A is supposed to be, unless they have to necessarily coincide. So both of these questions have to be answered positively if I want to have a chance at defining my tau of A. Yes?
This is a bit quick for me. So what do you have in mind with A naught?
Trace path operators.
Could you remind me of the definition of trace path operators?
Purely discrete spectrum, and the spectral elements counting multiplicity are absolutely similar. And then you sum them up, and that's your trace, just like in the matrix case.
Okay.
Now,
okay, and the difficulty is defining a trace for the ones that are not trace path.
exactly, because those are precisely the cases that we have. In the case where we have a Euclidean background, our operators are trace paths, so we just take the trace. If we have a lattice, they are matrices, so we have a trace. In our case, that means we have certain special cases, namely the set A0, on which the trace is defined, and we want to extend this because whatever we define our trace to be, it should coincide with the cases that we know are well defined.
And what is the role of phi here?
The role of phi is rather than looking at a single element A, I'm looking at a holomorphic family of them, which means that if some of these will have well-defined traces to begin with, then I can extend them analytically to the point that we want to look at. So later on, what this will mean is that if you have a quantum field theory, rather than looking at a single quantum field theory, we're going to construct a holomorphic family of quantum field theories. Some of those will have a vacuum expectation value defined in Feynman sense, and then we analytically continue those to the quantum field theory that we want to look at. So the choice of this holomorphic function is, well, rather not obvious. So before we jump into the operators that we're actually playing with, let's have a look at an example. And the example I want to look at is the absolute value of the derivative on the, well, 2 pi torus. In that case, we know the spectrum of the absolute value of the derivative. It's just the absolute value of the integers. So the trace formally is the sum over all integers mod n, which obviously is not absolutely convergent. So this operator is not trace class. Or I can write it down as 2 times the sum over all integers bit. Now, I want to introduce a complex parameter here. And I could do this, for instance, by raising my operator to the power 1 plus z. Now, if I evaluate mod d to the 1 plus z at 0, then I get back the operator that I started with. And if real part of z is less than -2, well, then our spectral elements are mod n to the 1 plus z, but this now is an L1. So the trace of phi of z is well defined, and those will be those guys. And we know the analytic continuation of this, namely twice the Riemann zeta function at -z-1. So in particular, I can evaluate this guy at z equal to 0, and I define the trace of my operator, which hasn't been defined at the beginning of the slide, as, well, precisely this value, which is -1/6. And that's also why we call it zeta-function regularization, because those were the initial examples that basically were written down. Now, the operators that we're working with are a little bit more complicated. So, what do we have? Well, I'm going to assume that our space-time is globally hyperbolic so that I can cut it into Cauchy surfaces. And in particular, I'll take one of them and call it capital X. Then the operators that we're looking at will be integral operators on the Cauchy surface X. And they have a kernel which is of this form. Again, this is a distribution, and generally we can't say any more. The important part is we have a phase function, which splits into 2 parts. There is a degree 2 radial part, whose coefficient I'm going to call h2, and there is a degree 1 part. Essentially, the degree 2 part will come from a second-order differential operator. The degree 1 part will be lower-order terms of that plus first-order differential operator. So if we're thinking about a fermionic theory, for instance, we would expect h2 to be 0 and only have the h1 term. And A contains further lower-order terms and, well, kind of things of omega and other stuff that's floating around. Now, the fun thing is, if our Cauchy surface is compact, then the trace of these operators is formally defined as the integral along the diagonal. If we have a trace class operator, then this is actually true. If we don't have a trace class operator, this may not make sense, but in a lot of cases, this will actually make sense as a distribution. It'll just not coincide with the trace because we don't have a trace operator. So if we take this as our ansatz, essentially, for the trace, knowing that if we have a trace class operator, this will be correct, then the integrals that we try to define are precisely those guys down here. And again, these actually make sense as distributions. They're not integrable, but that's where we're going to throw in the complex parameter in order to make sure that whatever this is, after we have a complex parameter in there, will give us something integrable, and then we want to do analytic continuation.
Could you explain the domain of integration?
It's essentially, which one? This one? Or this one?
The first one.
It's microlocal analysis. So if you're starting with a pseudo-differential operator, if it's a pseudo-differential operator, then this is just part of the dimension of the manifold.
Okay.
And for Fourier integral operators, the n may not be the same as the dimension of the manifold. So there can be shifts in there, but it's essentially that. And here it's just one. Now, the process of throwing in the complex parameter is called gauging. I know that is horrible notation or nomenclature, but that has been coined by geometric analysts long before I've been around. So I'm not going to change it now. The idea is, well, we want to add in a holomorphic family of functions. If we evaluate it in 0, the function shall be just the constant 1, because we want to reconstruct the operator that we started with. For everything else, there is some choice, but I want you to choose a G that is radially homogeneous of degree Z. What you do on the sphere bundle, I don't care. If you do this, though, then there exists a real number, capital R, such that the operator whose kernel I now define to be precisely the one that we started out with, but where the symbol is multiplied by this function G, this will become a trace class operator, which means the trace of phi as this integral will be well defined, provided that real part of Z is sufficiently negative. So in particular, we have an entire half space of complex numbers that we can extend. And now you have to do a little bit of work, because can we extend? Well, if the H2 part is 0, at least on the diagonal of x times x, then what you end up with is a Fourier integral operator zeta function in its very pure sense, and that's precisely what I've been looking at doing my PhD. So, if I may say so myself, we have a fairly good understanding of what's happening here. If the function H2 doesn't have any zeros at all, then 3-4 pages of calculation later, you can show that this function actually has a holomorphic extension to the entire complex plane. Well, in most cases, we're going to have some mixed case of these two, but microlocal mix and match. We break it down into the two special cases, and we sum them up with partitions of unities, microlocal. Which means that, yes, the zeta function of phi in 0 can be evaluated up to certain special cases, which come from precisely this guy, but they're well understood. And they're critical degrees of homogeneity in the very same sense that you would see them with pseudo-differential operators. And furthermore, these values only depend on the operators that we start with. So yes, we only have a single candidate for our extension, and if you really care, it's also trivial. In particular, we can now interpret these traces that Feynman came up with precisely in this setting. And that means that the quotients that we're looking at are, quote unquote, almost always independent of the choices that we make, because if these values are non-zero, then, well, we take two quotients of non-zero numbers which don't depend on the choices that we make. So this will be independent of the choices of gauge. If we have these critical degrees of homogeneity where we have poles, it turns out that these poles have to be simple, which means you're in the residue on residue case. And the residues themselves, they're called the residue traces. They're independent of the choices that we do. So that's going to be peachy as well. The only problem that you might run into is, what if you're in the 0 on 0 case? Because then you're taking quotients of higher order Laurent coefficients of these zeta functions, and they depend on the choices that you make. So usually we don't need to care about which functions phi we choose, but sometimes we do. And this is where I completely naively argue from physics and say the following. Say you have your favorite quantum theory. Then going to the operator side of this gauging procedure, there has to be a family of Fourier integral operators, called it capital G, such that if I multiply my time evolution with this family G evaluated at Z, I obtain a kernel of the form that I've been talking about earlier. Because U is a unitary, you can always make that happen. It's really just, if you take the G, take whatever operators you get and multiply with U to the -1. So we can construct such families of operators. Now, if I look at them in the range where real part of Z is sufficiently negative, such that Feynman's construction makes sense, then I can say that U times G evaluated of Z is a generalized notion of the time evolution in that theory. So the denominator is the partition function because it's a trace of the quote-unquote time evolution. And the numerator should then be the time evolution, which I've just defined as U times G times the observable that I'm looking at. And in that sense, I have now fixed a choice of gauges to be the same in both numerator and denominator, even though the traces to begin with were independently defined. Of course, this doesn't answer whether or not we are now independent of the choices that we make, but this, in my opinion, is the physically reasonable choice. And in that sense, I interpret this as defining a holomorphic family of quantum field theories precisely by taking the same Hilbert space in these time evolutions. And some of them will have a well-defined path vacuum expectation value in Feynman's sense. And then we analytically continue and define the vacuum expectation value in the theory that we're looking at by analytic extension. So let's have a look whether or not this actually makes any reasonable sense. And the first example that I want to show you is one of my favorite examples, and it's the free relativistic fermion in 3+1 dimensions. The Hamiltonian is probably fairly well known, and on the symbolic side it looks like this. The gauge function that I'm going to choose is incredibly inspiring. It's just the r to the z, because I don't want to play around with the rest of the function g, and because I have the choice to choose whatever I want to do, I'm picking this one because it's the easiest for me to compute with. Now, the observable that I want to look at is the Hamiltonian itself. So I can now plug everything into this zeta function divided by zeta function and obtain this wonderful little expression. Does anyone know what the outcome of this should be? I know you know what the outcome of that is. Anybody whom I haven't told the outcome of that before? Well, let's find out shortly. First thing we're going to notice is that if we are looking at the first term in the numerator and the denominator, up to a factor of MC squared, it's the same. So let's pull this guy out, and we're left with those guys. I've also integrated over the sphere because there's no explicit side dependence, so it's just volume divided by volume. Now, for those guys, well, here we have to think back a little bit. When I was showing you the kind of operators that we're working with, I said they have these exponential terms with these phase functions. They don't show up in here, or at least not obviously, but the sine and cosine can be written as sums of exponentials. So let's do that. Plugging in the sine and the cosine within their exponentials, we now have the form that we were looking at earlier. And if you stare at this for long enough, you will realize that those are analytic continuations of Laplace transforms of homogeneous distributions. Now, the good thing is we know what Laplace transforms of homogeneous distributions are, and we can plug in their analytic results. If you're wondering about the factors, I have to look them up too. In any case, we're now having this wonderful little expression here that we want to take the limit z going to 0 to. That's just some complex number, gamma of 4, t to the minus 4, divided by some other complex number, which is non-zero, times gamma of 3, times t to the minus 3. Whatever the heck this is, it's going to be proportional to 1 over t. And as we're sending t to infinity, we've just computed d is equal to mc squared. I like this example.
That's because you're in the vacuum.
Yes. Exactly. And other than this being a nice example, in my opinion, we actually learn quite a lot from what's happening here. Namely, the analytic continuation happens by means of analytic continuations of Laplace transforms. And this is generally the case. Now, it may be really, really difficult to get to this formulation, but it exists. So you can actually make a computer do these computations if you teach it how to do a Laplace transform of analytic of homogeneous distributions. So the next example I want to show you does exactly that. It's the topological rotor, i.e. a particle of mass m on a circle of radius r. We'll introduce the moment of inertia. The generalized coordinate is just the angle. The generalized momentum, something that even I can compute. And then we have the Hamiltonian being that guy. The observable, or one observable that is interesting, is the topological charge. Although the topological charge itself is not very interesting because of symmetry, expectation 0, but it's squared divided by minus IT for reasons that I once looked up in a physics book. Limit t to infinity will give us the topological susceptibility. And what I can do is I can plug this into SymPy. Literally, plug in the numerator and the denominator. If you're wondering why there are Fourier transforms, I'm evaluating in zero source, which is the fancy way of writing integral and forcing SymPy to use better libraries. Then we can take the chi-top and precisely as the limit that we want to see. And as you can see here already, the topological susceptibility is up to a prefactor, the energy gap. So if I run this in the background, I can pop back into my slides, and if my physics textbook didn't lie to me, then the result of that should give me the energy gap, which should be 1 over 2j. And of course, I wouldn't be showing it to you if it weren't, but the energy gap is 1 over 2j. So yes, this guy can do. But of course, this is a fairly simple example. So let's have a look at a little more interesting example. I'll run this in the background. Now, this is a spontaneous symmetry breaking. And here we're taking a slightly different point of view. Rather than looking at quotients of zeta functions, I only want to look at the partition function itself here. Mainly because I wanted to figure out whether looking at the partition function in isolation makes sense. So suppose you have scalar fields pi 1 through pi k, you have a Hamiltonian that depends on those guys, then we can define the partition function precisely in this zeta-regularized manner. Alternatively, I can say that this is the partition function with respect to an effective potential. And if I solve for local constant minimizers of the effective potential, then taking the limit t to infinity, those should give me the vacuum expectation values of the fields. And if I take the eigenvalues of the Hessian of the effective potential in the limit t to infinity, I should obtain the squares of the field masses. The easiest non-trivial example that I can think of is a 5^4 model, which has this wonderful little Hamiltonian here. And again, according to my favorite physics textbook, the vacuum expectation value should be plus minus square root 6 on lambda times mu, and the field mass should be square root 2 times mu. Now, the important thing here is that the partition function is defined via a zeta function, which means it is independent of the choice of gauge, and therefore it either works with any gauge that we choose, or it fails horribly with any choice of gauge. Now, in this case, we get minus and a plus square root 6 on square root lambda times mu, and the field mass square root 2 times mu. So it works. But of course, I wouldn't be showing it to you, right? So can we say something a little more general? And this is where the theorem that is currently in archive, hopefully soon to be published, with Call comes into play. Namely, we've been looking at this from a slightly more generalistic point of view and say, well, suppose you have a quantum field theory that is sufficiently nice, and whatever sufficiently nice means will be understood in a couple of slides. Then we've shown that we can introduce a discretization scheme and a very loose manner of discretization scheme, such that the continuum limit of this discretization scheme will, on one hand, give me a expression which defines vacuum expectation values in an axiomatic sense, but unfortunately is entirely useless for most applications because we don't know the vacuum. On the other hand, it will also converge to the zeta-regularized vacuum expectation. So not only does this discretization scheme make sense, but it also proves that the zeta definition, which is mathematically rigorous, coincides with the physical definition of vacuum expectation values. So even though we've been basically breaking physics quite a lot in constructing these guys, they do make sense. And even more so, this discretization scheme can be implemented on a quantum computer. So if you can, you do. The example that we've been looking at is a one-dimensional hydrogen atom, because this one is actually of maximal hardness for a quantum computer to solve. The plot that you see here is a noise-free. It means that the Hamiltonian complexity is maximal. And so this plot that you see here is a noise-free simulation of running this discretization scheme in qubits. And what we can see is a fairly decent exponential convergence, which kind of surprised us. Now, of course, on the hardware there is noise, and we've been running it on 1 qubit, which gave us around 5% error. On 2 qubits, we already ran into 100% error on last year's hardware. On this year's hardware, we rerun this. We got down on 1 qubit on 0.5%, and on 2 qubits in around 10% error range. So this actually does work on the hardware as well. But how do you map this? Well, first thing is we have the Hilbert space H. And we want to choose an orthonormal basis, which I'm going to call EJ, in a very specific manner. Namely, I need to be able to find another Hilbert space H1, which also contains my orthonormal basis, i.e. it's densely embedded, such that all my gauges acting on the observable and the gauges themselves are bounded linear operators from this embedded Hilbert space to the Hilbert space that I'm actually working with. And that shall hold true for at least the neighborhood, or z's in the neighborhood of the half space containing 0. Now, if you're thinking of H as an L2 space, then the general choice for H1 is some Sobolev space with sufficiently many derivatives. And because these will be pseudo-differential operators of finite order, you can find some number of derivatives that is high enough to make this do. Once we have this, we can write down the ortho projections onto the first n basis vectors in H and H1 respectively. I'm going to call them Pn and Qn. And that introduces a discretization scheme for my operators by conjugating with the projections. I do this for every observable. And so in particular, this discretizes the Hamiltonian, which means this induces a time evolution in this discretized setting. And it looks like this. Unfortunately, it is not just PNU QN, but, well, I have to live with that. Furthermore, it introduces the notion of a discretized vacuum by minimizing the symmetric form. Phi goes to the discretized Hamiltonian times phi in the sphere of the n-dimensional subspace. And if n is a power of 2, I can do this on a quantum computer, for instance, using a variational quantum eigensolver. And that's essentially what we did. Well, this means that we can, at least in some sense, find approximations on our vacuums. And once we have those, we can just take whatever observable we want and evaluate it on the quantum computer because we can generate an approximation of the ground state.
Over here, like you use like qubits as a basis for Hamiltonian of hydrogen atom.
Yes.
Spectrum.
Yeah. So in fact, for the hydrogen atom, we've literally used the Fourier basis. So 2 to the q Fourier basis vectors are in the basis that we're discretizing on. And well, so this tells us how to do, but it doesn't actually. Yeah.
We'll see Fourier basis in the regular direction.
It's on, yeah, it's only the spatial direction, so from -π to π. We're looking only at the hydrogen at -π. I mean, you can do it in -xx, for instance, and send x to infinity, but for the purpose of just running an example that is showing that it works, we just chose -π. And yeah, so this shows us how to do it, but it still doesn't explain why it works. And this is where we actually have to do a little bit of functional analysis. Now, if your quantum field theory happens to have an energy gap and the vacuum is non-degenerate in the continuum, then we can prove that taking care of a phase factor, these approximates of the vacuum will converge to the continuum vacuum. So this actually does make sense to be interpreted as an approximation of the vacuum on a quantum computer. Furthermore, if you now introduce an observable, and the assumptions that I wrote down there are basically just saying the operator yes is an observable and doesn't blow up your universe if you try to measure it, then this discretized notion of vacuum expectation value, as we would measure it on the quantum machine, will converge to the axiomatic definition of the vacuum expectation value. And so in that sense, this discretization scheme makes sense. On the zeta-regularization side, what we're looking at are quotients of these traces. Now, previously, in the continuum, I put the gauge operator onto the time evolution. And this is really nice in the continuum. However, I now want to switch my point of view and put it as an observable. These are equivalent statements, but what I can do now is I can express this quotient of traces that I want to look at as a quotient of vacuum expectation values. And in particular, all I'm doing here is essentially introducing a partition function divided by partition function.
So There's one real question. Like, where do you need like this in the hydrogen atom problem, like this regularization?
You don't. You will need it if you want to look at like time-dependent processes or something like this. But for a stationary process, you don't actually need it. It's just an example to show that the discretization will converge to this.
So it doesn't.
Yes, it's a convergence. Because you'll need it in the continuum.
And what's the connection with the quantum computing? In the sense that
it's that we can. The connection with quantum computing is that the zeta-regularized vacuum expectation. So where we have this, if this is the zeta-regularized vacuum expectation here, we want to take the same limit. And so what we can in particular say is that we can define the continuum vacuum expectation using the zeta-regularization. And so we have an analytical expression of how to handle the continuum case. And we have this quantum computable approximation to it.
But that comes on top.
That comes on top. That's, yeah, that was literally cherry. When we were looking at this, we basically tried to just show that this guy is equal to the zeta-regularized expectation definition. And it turned out that the method that we wrote down is implementable. So if we're looking at it from the zeta side, then now I want to look at those guys as part of the observable. And so we're taking quotients of vacuum expectations of two different observables. And that means if I look at them as a family of holomorphic functions, I can show that this family, under the assumptions on the observable that I've stated before, will actually be compactly convergent. Now, if real part of Z is sufficiently negative, those guys will converge precisely to those guys, because those guys are just the traces, as we have trace path operators. And so what we're doing is we're taking the trace path operator, we're truncating it to a finite rank operator, and we're taking back the limit. So on an entire half space, we know that this limit will coincide with this function, and because they're analytic functions, they have to coincide everywhere. So in particular, they have to coincide in 0. So if I evaluate this guy in 0, then I have from the last slide that the limit of the discretization is, well, the physical definition of the vacuum expectation, but it's also just g of 0 times omega divided by g of 0 expectation, because g of 0 is just 1. And that means that it coincides with this guy, which is precisely your definition of the zeta-regularized vacuum expectation. So at least on some abstract level, we understand why all of this makes sense. Furthermore, we can apply this on the lattice. And on the lattice, we're back in this picture where we want to write out our quantum field theory by, well, writing down the Lagrangian and taking the corresponding action. And usually, well, we would have to Brigg rotate because those integrals aren't integrable, or those functions aren't integrable. But now we have this idea of throwing in this complex parameter, so we can make this integrable through the complex parameter again. That means a quote-unquote zeta lattice QFT would start out in the way that you would start out with your lattice QFT with Lorentzian background. And then you throw in this complex parameter, which I'm going to put onto the amplitude. Now, you might ask, what happens if I try to put the complex parameter on the Lagrangian? And the answer is, provided that you stay in the algebra of Fourier integral operators that you're working in to begin with, you can always go back to the same Lagrangian. There's always a microlocal reformulation which gives you the same phase functions, and all the complex parameter will be on the amplitude. So this doesn't actually restrict us in any way, shape, or form. Now, the hard part is to actually get to the Fourier integral operators. And this means that you will have to construct a family of Fourier integral operator whose nuclear traces are distributionally equivalent to whatever this guy is. It's fairly straightforward. It's not easy in the sense that you just sit down in an afternoon and do it, but if you understand how to map between the two, it is not overly hard either. So it's a lot of work involved, and you're probably going to make a lot of mistakes in your computation, but it will not require many tricks to think about. So we have a reasonable shot at getting to this expression. And once we have it, well, we are back at these interior integrals, which are Laplace transforms of homogeneous distributions. So if our theta, the phase function, doesn't have any zeros, i.e. if physics is nice to you, and it turns out all the cases that I've looked at so far are of this form, doesn't mean that they all will be, but at least everything that I've seen so far, then, well, you just take the analytically continuous Laplace transform, you plug in your theta, and you take this expression, you plug it back into the last equation on the last slide, and we have that both numerator and denominator are expressions of this type. And if we think back, we started out with something that is numerically ill-posed because we're trying to integrate functions that are not integrable numerically. And we end up with a series, some gamma terms, and an integral over spheres, high-dimensional, but these are continuous functions. So yes, this is still a very difficult problem to solve numerically in general, but it's a well-posed problem. And this is a big step forward, in my opinion, because suddenly we can talk about problems where we can, where we cannot Wick rotate and we can actually address them on the lattice. Of course, you might ask what happens if physics is not nice to you. Well, in that case, you want to look at the Laurent coefficients of those guys. And as it so happens, I computed those in my PhD thesis. If you're in the residue case, then the residue is precisely this guy. Looks horrible, but it's a finite sum over integrals of spheres of continuous functions, so everything's fine. If you're in the 0 and 0 case, then you're looking at higher order Laurent coefficients. In which case, well, what do we have? We have a principal value integral of the ball. We can do that. We have a bunch of sums of a bunch of factors and integrals of continuous functions over spheres, fine. And more sums, integrals of continuous functions over spheres. This is still doable. Of course, it's not nice, but it is doable. So, what have we got? Well, we actually, by random chance, essentially, ended up with a mathematically rigorous definition of vacuum expectation values in the continuum for cases where the physical approach doesn't work in the naive setting. However, we've done this by extending Feynman's approach. So what we've done essentially is we took Feynman's formula and extended it to the cases where it doesn't work. And this includes quite a lot of cases which are interesting. If we apply this to lattice QFT, then we obtain a formulation of lattice QFT, which we can use in Lorentzian backgrounds, i.e. we can look at time-dependent processes, for instance. And furthermore, we have a discretization scheme, which is accessible using quantum computing, which is quite nice. Now, what do we need? Well, we need quite a lot of things because all of this is essentially undeveloped. First of all, if we want to do quantum computing, we need better quantum computers. Current machines are very noisy, so we'd like to have more qubits, less noise. However, that's actually not the part where I consider much of a problem coming forward, because if we look at the advancements in hardware that we've seen over the last year, they are orders of magnitudes on our results. So if that even remotely continues in any sense like that, this is not going to be a problem. but we need better quantum and hybrid algorithms because, well, we're trying to do quantum computing on interesting problems. So we actually want to do something that converges quickly and maybe keep the noise down and get nice results. And all of these are very hard things to ask for, at the moment at least. And of course, if you say, well, I don't care about quantum computing, but what if we want to do classical computing on the lattice? Well, in that case, you're trying to integrate over high-dimensional spheres. And the high dimension is in the same order of magnitude as the dimension that you would get if you wanted to do a Monte Carlo simulation on whatever you're trying to do. So these are really, really high-dimensional spheres, and to my knowledge, there aren't any really applicable methods there. So better integration techniques on high-dimensional spheres is something that we really like to see here. And yeah, with that, I thank you for your attention.
So, questions?
So the lattice QCD part, you can avoid the sign problem also if that appears, or?
Well, these integrals these are continuous functions, but they're complex. So depending on your integration techniques, yes and no. It will not show up in the same way that the sign problem shows up canonically, but there will be similar effects.
Shall we regard like what you presented as in a way of making mathematical sense of Lorentzian factorial, or
that's how I see it, yes.
Or as a practical numerical?
I see it as a mathematical way of making sense of them. I think that's the primary.
If I were to take like one message from this, like this could mean that this may be a way of defining the mathematical properties of sense, a Lorentzian integral.
Yes.
But does it have any bearing on this field of algebraic on the field theory?
Yes, because
I have the impression that like algebraic on the field theory is how like in some cases makes statement that Lorentzian on the field theory makes mathematical sense. So what's the relation? It's about the particle formulation.
So there are essentially two relationships there. First of all, if you're working in the Hamiltonian picture, then you need the algebraic quantum field theory, the axiomatic quantum field theory to be defined in the first place. So you need the operators to be defined. And this is a big part of what axiomatic quantum field theory does. So I'm basically working on top of that step. However, on the other hand, a lot of the cases that are considered in axiomatic quantum field theory, people will try to take these traces. And one way that people take traces of unbounded operators is they look at differences of unbounded operators, which will be trace class, and then they can take the trace. Now, using the zeta-regularization, I don't have to take the difference. I can actually split the two traces apart, and then the trace of the difference is just the difference of the two zeta-regularized traces, which opens up ways of, well, working with these kind of things.
So if you look at the free quantum, I'm sorry for the ignorance. If you look at the free quantum field theory that everybody understands or sympathizes with, where like we calculate expectation values at Hamiltonian, and we get an infinity race. If you work in momentum space, right? We get an infinity values for the fact that there's like a 0-point energy for each momentum mode that adds up to infinity. Then if you look at some extended state and we calculate expectation value, it's also in a scientific problem. We might take a difference between these expectation values and get something hopefully physically meaningful. So like that's one approach. But like in this approach, it's not that like any in principle like none of the traces make sense, right? They're equal numbers, but the difference of traces of the same operator in two different states was something that was meaningful.
Yes.
So
And
over here, like, I have the impression that somehow like, you want to make sense out of a single trace, right? Like,
yes, exactly. That's where the method comes from. So rather than having to take the difference of the difference and then take the trace,
yeah.
I can now make sense of each trace independently. So even so, the infinite vacuum energy,
yeah.
This one would now get a finite value. Now, of course, I can still subtract that from whatever the value I get from the other side, and I will precisely get the same difference. But having the option of actually giving this infinite number a finite value gives you options, and that might feed back into different ways of dealing with problems.
I think in our, I'm not sure I should say in our field, there's like a vast expertise in this room, but like at least like for people who apply like script theories, so like subtraction, like there's been like this great interest in this technique of localization, under this supersymmetric localization, right? And I'm not really an expert on it. I think at least like maybe somebody in this knows much more about it. But the idea was that like, we have a pattern of some complicated supersymmetric field theory, and then if you put it on some very particular manifold, for example, on S4, if the theory is four-dimensional, then you can evaluate the pattern, and then basically the result like is some meaningful number, whether like minus something, and you get this straight as your face without any issues of deregularization, but just like some trick of basically writing this integral as like something like an exact integral and getting the result. So what I'm saying is that this is something that is like very algebraic. It looks like a very algebraic approach to operating with integrals, and somehow do not have to deal with like all these issues of deregularizations. And in the end, you get a number, and this number effect is a meaningful number that you want to interpret. So, like, have you thought about like this machinery?
I'm aware that these things exist. I haven't had the chance of looking into any of that.
I mean, like, I'm saying this because the argument in the textbooks is that, like, oh, like, say we have the expectation value of Hamiltonian and Gauss, like, oh, it doesn't really mean much, right? Unless we have a coupling to gravity. And the only thing that matters for us is the difference between expectation value to space. Like, over here, we seem to be saying, okay, let's assign some meaning to, or at least a mathematical sense to expectation value of a Hamiltonian state, right? And typically, we do not encounter this. On the other hand, like, there's this many local implementation this supersymmetric equalization that somehow goes along these lines in the science some numbers to expressions that otherwise you might be tempted to say that are not that interesting.
I mean, in this sense, I've really been looking at essentially I started out as this is looking at an example, right? I was basically trying to find examples for the zeta functions that I could work with. And it turns out in the sense that we can use Feynman's approach that gives you infinite values if you follow it strictly. And by doing this, you will get correct values out of it. So it essentially makes sense of Feynman's formulas in the thermal limit of the traces.
But like two more questions. So in relation to algebraic field theory, you'd say that algebraic field theory is like somewhat independent from Feynman's approach, and like what you do is somehow like make sense, mathematical sense of potentially ill-defined particles.
I don't say that it's independent of Feynman's approach. What I'm saying is that they're trying to do something similar, as of making sense of what these things are supposed to mean.
Yeah.
And this is a different way of making sense of what these formulas are supposed to mean. I haven't had the chance of actually going into the different methods that they do in axiomatic quantum field theory and see how they relate to this approach. I suspect that quite a lot of them, there will be some relationship, and once this has been explored, there's probably some interesting knowledge to be gained as to how they relate to each other. But I don't know that at the moment. And
the second last question for me, and MC shut me down afterwards. So suppose we do like free scalar field, like we think on the lattice, but we look at quantizations, like multiples, right? Like we are on a circle, so we have like a finite number of frequency variables, right? We quantize and we calculate the expectation value, we get something like, and we see that like as we take the numerical into account, we get the perfect result. Like is what you're saying like really bound to particles, or you can also try to quantization?
This is essentially based on path integrals because it takes the distribution, which is the path integral, and it regularizes it in the sense that the formulae that you get make actual sense with the regularization. Again, I presume that there is correspondence with other regularization methods, but I don't know. I haven't looked at them.
Another question. Sorry. The last question for me. So what I understood from your approach is that you were trying to, the strategy is to make sense of this by finding an analytic continuation such that coincides with the trace whenever you know that how to deal with the trace, and otherwise we can't how to define. For the case of the expectation value of the Hamiltonian of the vacuum, as Michael was saying, you got M, right?
Yes.
For the case of the fermion.
Yes.
But in that example, the calculation of the expectation value of the energy, as Michael was saying, in all cases that I know, except supersymmetric Lagrangians, the expectation value, that expectation is infinity. So to what are you matching that particular? So what is the A0?
The A sub 0 is so.
In this case, do you understand?
In yes. So
right.
So if you take this Hamiltonian, you take this matrix or this symbol, you raise it. You take the time evolution, that is the C0 group that is generated by this Hamiltonian.
Okay.
That has a kernel. That kernel has a phase function. And that phase function defines an algebra of Fourier integral operators. And the intersection of that algebra of Fourier integral operators with trace class operators on L2, that is your A sub 0.
Okay. Maybe if I understand your question correctly. So what this do is it gives well-defined value for the ground state energy. This is not the physical value because the ground state doesn't have a physical value.
Yeah.
So you still would have to compute the energy to get really a physical quantity.
Right.
But it generates for you, if we put it on the quantum computer, for example, it generates for you the ground state energy, the ground state wave function. So in this ground state wave function, we can measure local observables or correlation functions or whatever. Okay.
Okay.
So we get a number. It's like with the Riemann zeta function. You have still an infinite sum, but if you evaluate the Riemann zeta function at z equals 0, you get a well-defined number. And we provide you a well-defined number. And if you would now compute the next energy level, we will get the ground state, the gap, the mass gap.
And so the number itself doesn't have any physical implication.
No, you can arbitrarily shift the vacuum energy.
So you're after the wave function of the vacuum.
We are after providing well-defined numbers for the ground state energy. They are not physical, and we have examples where we have these divergences that we need to subtract, and this comes out in this approach automatically. So I think that's the idea. And then we get the wave function, ground state wave function, in Lorentzian framework in the past. Simply fantastic.
Okay, so if there's no further questions, I Thank Tobias again.